Okay, so I'll be taking voltage regulators, and we are going to discuss four things here, like what is a voltage regulator and where do we use them, and its terminals, and we'll get to know about an example of it. So let's proceed with the voltage regulators. Okay, so first of all, what is a voltage regulator? Like it is written here, a voltage regulator is an electrical device or circuit that maintains a stable output voltage regardless of variations in input voltage or load conditions. Okay, so the primary purpose of using this voltage regulator is to regulate the output voltage. That no matter whatever input we are giving it to this input port, voltage, no matter whatever input voltage we are giving it to this input port, this voltage regulator maintains a constant DC voltage across its output terminal. Okay, so and these are basically used in various electronic components. Like we have so many components in electronics which are voltage sensitive. So in order to prevent them from getting damaged, and they are made so that they operate on a certain voltage. So these electronic components are not cannot afford to have a voltage fluctuation in their input side. Okay, so to give them a regulated constant DC voltage, we use voltage regulators before its input. Okay, so is this thing is this thing clear to you all, that what is a voltage regulator? Like a basic idea, like voltage regulator is used for maintaining a fixed voltage. Okay, okay, let's proceed further. So, where are these regulators used? So, in electronic devices like smartphones, laptops, or power supplies, we see we need to ensure a stable voltage for sensitive components, as we told earlier in this previous slide. So, voltage regulators are used in these cases, like in smartphones, in laptops, in various circuits, they are used, widely used. Okay, and one more thing that we see in our vehicles, we have batteries. Okay, so what if we speed up our car, and our car have dynamo system? So basically battery gets charged using that dynamo generates voltage, and the power delivered by this dynamo is used to charge up the battery. Okay, so voltage regulators are used in the vehicles for this purpose also. Like if we speed up the car, so the voltage will rise up because the dynamo speed is also getting high now. Okay, so if dynamo is generating more voltage, should the battery start charging at a higher rate? Can anyone answer? Like if we are giving it a higher voltage battery to the battery, so should it charge at a higher rate? Answer, please. Please respond. I think this will be okay. No, no, obviously no. Yeah. So the answer behind this thing, that we have a application of voltage regulators in the cars also, that we need to maintain an optimum charging voltage for the battery, that it should not exceed a particular voltage. Okay. So if that voltage exceeds, so the battery may get damaged or heat up so quickly that it won't work further. Okay, so we have this application in a car also, that battery gets charged and voltage regulator is put into the circuit before charging this battery. Okay, okay. Now the third application, this one is very crucial. Voltage regulation is, we have one LM7805 IC. Okay, this one is a voltage regulator IC. This is just an example of voltage regulator IC. Okay, so let's let's see its pin diagram first. So we have these three pins. These three pins are in this 7805 IC, and pin number 1 is the input pin. Okay, pin number 2 is ground, and pin number 3 is output. Okay, so we are going to give input to this side, like pin number 1 and pin number 2. Pin number 2 is ground, which is common in both output and input side. Okay, so we have to apply input source here. Let me use this. Yes. Okay. Huh? Okay. See. Okay, so we are going to give input to this side, okay, input side, and we'll obtain output at this side. So this is the output side and this is the input side, okay. So this is very simple. Let's move further. Um, okay, so as voltage regulators are available in various forms, in variable output voltage. So we have various output voltages for our voltage regulators. So engineers have standardized a nomenclature for it. Like if it is written LM7805 here, so it means something. Okay. So do you guys have any idea from previous knowledge or like something like why it is written 7805 or something? No idea, no? Okay. Um, I'll tell this to you. Okay. Uh, okay. Let's go to the nomenclature. So here, first two digits. This prefix 78. Okay. These are this is the first two digits. So 78 represents fixed positive voltage regulator. That means that if here it is written 78, this means that we are going to get positive voltage at this output side. Okay, and here it is, if it is written 79, then it means that we'll get a negative voltage. Okay, so this just signifies that 78 means we'll get a positive voltage with respect to ground. How are we saying that this is positive or negative? With respect to ground. So ground is always considered as 0 volts. Okay, so ground is 0 volts with respect to this. This terminal is positive, then it is 78, and if this is negative, then it is 79. Okay, and last two digits. So last two digits represents the regulated DC output. Okay, so if it is written here 05, so that means that we'll get 5 volts regulated at its output port. Okay, so if this IC is 7805, can you guys tell me what is the output voltage? 5 volts. Okay, and is it positive or negative? Positive. Why? Yeah, it is written here 78. So that's why it is positive voltage regulator with an output voltage of 5 volts. Okay. Okay. Similarly, if it is written here 909, then it represents 9 volts regulated DC output. And if it is written 12, then it is 12 volts DC regulator output. Okay. So this is just a basic nomenclature. Let's move further. So till now we have discussed fixed voltage regulator. As you guys can see, like if it is 7805 IC, can we obtain like any other value like 6 volts, 7 volts, any other value using this IC? No, this is just 7805 fixed voltage regulator IC, so we can only get 05 volts. Okay, let me tell you one thing, like if input, this thing is very important, please understand this. If input we are giving like if we are giving it 7 volts, let's say, okay, what output we'll get? No, if it is 7805, 5 volts, okay, so we'll get 5 volts, okay. This will maintain 5 volts, but unless it is not dropped to that much extent, like if it is 10 volt, then also we'll get 5 volts. But if we give it 2 volts, then it will not give 5 volts. Okay. So the output voltage, so the input voltage has to be higher or equal to this output voltage, output maintained voltage. Okay. So actually it follows a curve here. This regulator IC follows a curve. Okay, let me clear this thing a bit. Okay, let me write it here. Okay, so this DC LM7805 IC follows this curve. Okay, here it is current, and here it is voltage. No, sorry. Let me erase this thing. If this is V input, okay, and this is V output. Okay, so this is the maintained output voltage. Like in this case, we are saying it is 5 volts. Okay, so it follows this curve. Like above 5 volts, it will maintain this constant voltage 5 volts here. Okay, but if we drop down this voltage below this, so we will not get this 5 volt here. We'll get something else. Like if we are applying something lower voltage, we'll not get 5 volts here. Okay, so these are some basic things. Are you guys getting these things? Okay. Okay, let's proceed further. Okay, so we had fixed voltage regulators. Like we cannot use 7805 voltage regulator IC to get an output voltage of 6, 7 volt, 8 volt according to our requirement. Okay, so what if we want to have output voltage according to our need? So we are using LM3170 IC here, which we can use to get a variable voltage according to our need. Like we can get any voltage according to our need. So let's read out this thing first. LM3170 has this ability to provide an adjustable output voltage. By using external resistors, you can set the desired output voltage, making it versatile for a wide range of applications. Okay, so let's understand this thing. So this is the LM3170 IC, and in order to use it as a variable voltage regulator, we have to use some resistors externally, resistor combination externally. Okay, so we'll use some resistors along with this IC. Okay, and we'll get voltage according to our requirement. Okay, some more advantages it has. So it provides relatively precise and stable output voltage, making it suitable for applications where tight voltage control is required. Okay, and this point is a bit important. It includes built-in thermal regulation. Like if it gets heated, if the IC gets heated, like if we draw so much current that it gets heated, so this IC will automatically drop its output voltage so that in order to cool it down. Okay, so it has built-in feature like if the temperature rises above a threshold, certain threshold, the IC reduces the output voltage to prevent damage. Okay. Okay. So do you guys have any doubt in these three points? Any doubt? Silly one? No, nothing. Okay. Let's proceed further. So, variable voltage regulator. How are we going to use them? Let's understand this now. Okay. So this is the IC LM3170. Okay. And this one is suppose pin number 1, this is pin number 2, and this is pin number 3. Fine. So this is the input side. This side is the input side. Okay. And this one is the output side. Okay, so this one is the input side. We have to use a source to power up this IC. So here we'll put some source, input source, and this is the output port. Ground is common in both, as we used to, we have seen in the LM7805 IC also. Okay. So now the characteristic of this IC is that whatever input voltage we are giving it to its input port, it will always maintain 1.25 volt or certain a characteristic voltage V0, let's say. It will always maintain a certain characteristic voltage across its output port. Let's say this is V0. In this case, it is written 1.25 volts. Okay, so okay, so we are using this property of this LM3170 that it maintains 1.25 volts at its output terminal. Okay. So we are using this property and try to achieve that thing that try to achieve any sort of voltage which we require. Like we can have variable voltages, like we can obtain 5 volts, 7 volts, 9 volts, 12 volts, 13, 14 volts. So we just need to change this voltage, this resistor combinations. Here we are using 2 resistors, as you can see. Okay. So let us understand this thing a bit. Okay. Is there any doubt in this portion, like how are we giving input and how are we obtaining output? Okay, is it clear to all? Okay. So we are going to use two resistors here, okay, R1 and R2, and this is again the input side. It is just the pin number 1 and pin number 2, okay, input side, and this one is the output terminal again, and we are using R1 resistor across this pin number 2 and pin number 3. Fine. So we are using R1 resistor across these two pins 2 and 3, R1 resistor, and this pin, which is pin number 2, is connected through a resistor to the ground. Okay. So this is the just the configuration. Just remember it and we'll understand how are we going to use them. Okay. So this is the configuration that we use R1 here in between pin number 2 and pin number 3, and this pin number 2 is again connected to another resistor through a ground, and which is connected to a ground. Okay. So do you guys know voltage divider rule? Okay. Voltage divider rule. Okay. So let me have a quick recap if it is required to you all. Is there anyone who doesn't know voltage division? Or is there any need to recap those things? Fine. Okay, so everyone knows voltage divider rule. Okay. Okay. So if this is the V out voltage, potential at this point is V out, and we are trying to figure out the voltage at this point, a potential of this point. Okay. So we can apply voltage division rule here, like this resistor R2 upon this combination R1 plus R2, okay, times this V out, potential of this point. Okay. So this is just a voltage division rule here. So this is basically the potential of this point. If we can, let's say this is point A. Okay. So potential at point A is R2 by R1 plus R2 times V out. Okay. We'll use this data and do some mathematical, very easy calculations. Just be with me. We'll understand it. So V out is the potential of this point. Okay. If we are like, let's take an example. If we are having a resistor and point A and point B, okay, and we are asking you what is VAB. Okay, so pardon me for my bad handwriting. So VAB can be written as VA minus VB. Okay, fine. So this is just a basic thing that we just subtract the potential of these 2 points and we'll get the potential difference. Okay. So we are trying to get the potential difference across this R1 resistor, and so we are just doing this V out minus VA, like VA is R2 by R1 plus R2 times V out, so we are directly putting it here. So V out minus VA is equal to, that should be equal to this V naught. Okay, are you guys getting it? These 2 points are, and if we take the difference, we'll get a potential difference which is equal to V naught. Okay, in this case you can say 1.25 volts. Okay, but we are generalizing it for V naught. Huh? Okay, yeah.
Use this rule R2 upon R2 plus R2 when both the resistors are parallel.
No, actually this one is the voltage division rule. Like, let me tell you first. Okay. Actually, this is not the equivalent resistance formula. Let me tell you this here. If we are having, this is just a voltage division rule. Let me tell it once again. Please sit down.
You can use it.
Okay. No. Okay. So if we have two resistors connected to a battery, okay, let's say the EMF of this battery is E, okay, EMF of this battery is E and resistance is R1 and R2 respectively, okay. So if we are asked to find out the voltage across these two resistors separately, let's say this point is A, B and this point is C, and we need to find out the voltage across this resistance R1, okay. So we can say that VAB, okay, this one is equal to R1 by this resistor series combination R1 plus R2 and multiplied by this EMF which is applied to the both to this end of both resistors, okay. So multiplied by EMF. So this is voltage division rule, okay. Okay, so you are asking. Oh, that's a good question. Okay, so we also had this confusion in our time. So let me clear this. So why it is written R2 here? You are asking. So see, if this point, like if this VA, we are trying to figure out VA, potential of the point A. Okay. So what is VA? Actually, VA is like, if we can say what is voltage across VR2. Okay, VR2. Let us use this. Okay, it is something like this. This one is connected to ground. Okay, and this point is here, which is point number A, and this is V out. Okay, and this is VA, and this is at 0 volts. Okay, so what is the voltage across this resistance? Let's say this is VR2, and VR2 is equal to VA minus this voltage. Okay, so VA minus 0 volts. Okay, so we can say that VA is equal to VR2. Okay, so we are directly, if we have to find out VA, we are needed to find this VR2. So VR2 is R2 by R1 plus R2 times V out here. Okay, hope this is clear now. Okay. Okay, so we were discussing this thing. So here the potential of this point V out minus potential at this point VA is equal to V naught. Okay, and if we do some mathematical calculations here, we'll directly get this result. V out is equal to V naught times 1 plus R2 by R1. Okay, so here we see V out is dependent on V naught and this resistor combination R2 and R1. Okay, so can you guys tell me, is it in our hand to change V naught? No? Why? Yeah, it's fixed. Actually, it is a characteristic voltage of this IC. We cannot change it. Okay. So what's in our hand in this equation? What we can change? R2 and R1. Okay. So by changing this thing, R2 and R1 combination, we can vary this voltage V out. Okay. So we can meet our requirement, like we can obtain any voltage V out by changing this combination and multiplied by this characteristic voltage which we can't change. Okay, so we can change R2 and R1 and get the required voltage. So this IC follows this equation. Okay, do you guys have any doubt in variable voltage regulator LM3170? डायरेक्ट R1 का वोल्टेज किस लिए, मतलब हाँ निकाल सकते हैं, R1 का भी वोल्टेज निकाल सकते हैं. हमने यहाँ पे बस ये इक्वेशन को यूज किया है V आउट और V नॉट R2 R1 के बीच में रिलेशन फाइंड आउट करने के लिए. ठीक है, You understand? Point A, this point A. No, actually, this is not ground now. That's actually a good question. See, if you guys see here, this pin number 2 is ground. I have written ground here, but now here it is not written ground. Okay, so we cannot say that this pin number 2 is ground now. Rather, ground is here at this resistor. Okay, so this is just pin number 2 now, and here the pin number 2 is grounded. In this case, pin number 2 is grounded, and this case, pin number 2 is not grounded. Okay, this is not always the case that we don't say these things that pin number 2 is always grounded. According to our requirement, we can change it. Okay.
Where is that wire?
This wire. Okay, so this is input port. We can connect a battery or like let me show you. Okay, so we are having 3 terminals of this IC. Okay, this one is output side, and it is like here it is a resistor, and this is grounded. Okay, and this is the input side. Let's focus on this part only. Okay, so this is input side. So we can connect a DC power source. Like we can connect a power supply here. Let's say it is a battery. Okay, of 10 volts, and the resistor combination chosen here, let's say it is chosen so that it gives V out of 7 volts, let's say. Okay, so here we apply some input source to this side. Okay, like we are applying 10 volts here, so we'll get corresponding output to this, and this is fixed, and this depends on this resistor combination as we saw in this equation. Okay, so this port is used for the input side. Okay, any more doubt? Fine, let's proceed further. Okay, don't be scared of this thing. This is just the internal circuitry of LM7805 IC. We don't need to remember this thing, even I didn't, and let's try to understand it a bit, not getting much more into deeper of this thing. Okay, so do you have any doubt? LM. Okay, even I don't know actually. Let me search it. Basically, these are all engineers. They are trying to nomenclate these things. And you didn't ask me that thing why 78 and 79 is used. Why not any other number? Okay. What is LM here? Okay. So LM prefix stands for linear monolithic. Even I don't know its meaning. So you can search it on the internet. Okay.
In the next class, we'll clarify.
Okay. In the next class, we'll clarify. Okay, let's try to understand this circuitry a bit. Okay. Like we have this input side, we have output, and this is common. Okay. This is internal circuitry of LM7805. We have so many transistors, Zener diode, resistors, this transistor, Zener diode. Okay. So we'll not go deeper into it, but we will just try to understand this thing. Like input is connected to this Zener passing through this resistor. Okay, so you guys might already know that Zener diode can also be used as voltage regulator in your class 12. And I want to ask you one question. In which bias are these Zener diodes are used? Forward bias or reverse bias? Reverse bias or forward bias?
I can see some of them saying bias.
Come on, forward bias or reverse bias? Reverse. Okay. Okay, so the correct answer is reverse bias. Okay, let us understand a bit. Okay, let us understand a bit Zener diode also. Is this thing visible to you? Is it visible to everyone? Yes. Okay. Suppose we have this Zener diode here, which is connected through this resistor to a battery, let's say, variable voltage supply, let's say. Okay. And you guys may already know that Zener diode has some characteristic voltage called as Zener voltage. Okay. It's already given in the JEE questions, like Zener voltage comes with the voltage of 6 volts or 7, 8 volts. So let us say this Zener voltage is 6 volts. Okay. Zener voltage, let's say this is VZ. Okay. This is 6 volts. And this is a variable power supply. And let's say it is fixed at 10 volts, for example. Okay. So this, oh, one more thing. This is forward bias. No, we have to do it reverse biased. Okay. Okay. We use Zener diode in reverse bias. So here this terminal is positive. Positive is connected to the negative side of this diode, and negative side is connected to the positive side of this diode. Okay. So this is reverse biased. And if we use this 10 volt supply here, so the Zener will maintain 6 volts across its terminals according to its Zener characteristic voltage. Okay. What about the remaining voltage? Like 10 volt is applied here, 6 volt is dropping across this Zener diode. So voltage will drop across this resistor also. And 4 volts. Yes? 4 volts. So we'll get 4 volts here. Okay. What if we increase it by 2 volts more? So Zener will still be at 6 volt. Okay. And this voltage will 6 volts. Will be 6 volts. Okay. So here you can see that Zener diode is working as a voltage regulator. Okay. So yeah, that's just basic thing to understand. Okay. So. So Zener diode is a voltage regulator here, and here is some complex circuitry along with this, and this circuitry maybe they work as like to make it more stable. Okay, like you guys also have seen this thing. I don't know why I'm getting so much into this Zener diode, but let me explain this thing. It's a very basic thing. Okay, you might have also seen this Zener diode characteristic curve. Like it follows this curve here, okay, in reverse bias, and this point is called as Zener breakdown voltage. Okay, so this is Zener breakdown voltage. Okay, so if you guys see, like this thing is I current and this is voltage. Okay, so voltage is getting constant. We are getting a vertical asymptote like thing here. Okay. So voltage is getting constant here and the current rises. As we apply more voltage here, the current changes, but the voltage across this diode will still remain sort of constant. Okay. But if we zoom in to this thing, still it changes a bit. Okay. So this is not that much stable. Even if we increase 12 volt, like if we are increasing it to 12 volt, like if we increase it to 15 volts, the voltage might change and get to 6.004 volts, something like that. So voltage changes. Like if we apply 18 volts, it might get changed to 6.114. Okay, so it might change, but that to not that much extent. But it will change. So in order to stabilize Zener diodes, we have this complex circuitry along with this. Okay. So we are done with this internal circuitry. We don't need to understand more into this. Let's proceed further. Okay. Do you guys have any doubt in this voltage regulator thing? 7805 or the variable voltage regulator? Anything? Fine? Okay. Any silly doubt? Yeah, please ask.
What about LM79?
LM79. Okay. So 79 stands for negative voltage. Like if this IC 7905, let's say, Okay, we are giving it input to this side, and we are obtaining output from this port. Okay, so what it does that this point is ground here, and if we are giving it some input, let's say we are giving it 10 volts, and this 0.5 means it will maintain 5 volts at the output. Okay, so 5 volts at the output, but 7.9 represents negative sign. So we'll get negative voltage here. Like if we use multimeter here and measure the voltage across this port, we'll get a negative 5 volts. And with respect to what? This ground. Ground is always considered as 0 volts, so this will be negative 5 volts. Okay, this is the significance of 7.9 or 7.8. Okay, any word in voltage regulator? Other than 78 and 79. Basically, we are just discussing 7.8 or 7.9 series here, or LM3170 variable voltage regulator here. There might be some more voltage regulator ICs also present in the market, but for our projects, we generally use this 7.8 or 7.9 series. LM3170. 7.8 is more efficient too. Actually, LM3170 is more efficient. It has some. We are using it like fixed voltage we require. That doesn't mean that it is inefficient. LM7805 works very well, and if we have to use it in fixed voltage, like we have to power up this Arduino, let's say this board. If we have to power up with 5 volts and we have voltage supply of 7 volts, 8 volt, 12 volt adapter. So in order to give it 5 volts to this input, we can use 7805 IC so that it can directly give it 5 volts. Okay, we can also use LM3170, but we have to use resistors also. Okay. Yeah, 78 series is also efficient. We can use it, and we generally use it in our projects. Okay. Okay. Any more doubts in voltage regulator? Actually, we use it as a voltage variable voltage regulator. If we have to use it like in any combination of resistors, we can use it like we can obtain 7 volts, 7.5, 8 volts, anything. It follows that equation that we discussed here. Okay. So we use this IC also, and this has some more advantages, like it has temperature protection thing also.
No, I was just saying that as the last letter T has it.
Okay, T.
Is having some significance or it is just.
Okay, let us clarify this into the next class. Even I don't know. We just use this IC, and we should more focus on the application part of this IC. And nomenclature, actually, we have to see it, whether the T signifies anything or it is just for.
I just wanted to know, does that T has any significance with that output?
Then output.
Or that out view?
VO.
I was just thinking that T is having some connection with the output.
Okay, no, I don't think so that T has any relation with this VO, because it is 1.25 volt, and there might be some significance. We have to check it on the web. Okay. Any more? ग्राउंड को कैसे कनेक्ट, अगर ग्राउंड को कनेक्ट कैसे करेंगे? अच्छा, ओके, सो एक्चुअली सी ग्राउंड को हम ऐसे कनेक्ट करेंगे कि यहाँ पे कोई भी रेजिस्टर है. ग्राउंड बेसिकली हमारे सर्किट में सिर्फ और सिर्फ एक कॉमन टर्मिनल है. जैसे कि हम इनपुट साइड में भी जा रहे हैं, अगर इफ यू आर गोइंग टू दिस इनपुट साइड, वी आर जस्ट पुटिंग दिस थिंग कॉमन टू बोथ द पोर्ट्स, इनपुट एंड आउटपुट पोर्ट्स. सो हियर ग्राउंड इज जस्ट अ reference point here, that if we are giving input to this terminal, so this point is automatically considered as ground, and which is common to both input and output side. Okay, so there is nothing like we have to connect it to the earth or we have to give it earthing. No, that's not required. Actually, it is just to say that this is common to both the ports. It is already understood that if it is ground, so This terminal is common to both. We just need to make it common. Why it is at 0 volt? Actually, voltage is also not a absolute quantity. We cannot say that this I'm holding this piece, so it is at some voltage. We cannot say that it is at 7 volts. We always define voltage difference, potential difference. Sorry, potential difference we always define. Like if any junction we have, if like we are having this port, we are saying this is V out. But with respect to what? With respect to ground. We are considering ground at 0 volt. That's not actually at 0 volt. We only say that this is a reference point. Okay, we always define potential difference. We don't say that this ground is at 0 volt. We just assume that if it is 0 volt, then with respect to this, everything is at another voltage. Okay. Okay. So, any more doubt in voltage regulator? Fine. Okay, let's move further and start with DPDT. This one.
Take a short break within 15 minutes.
Guys, let's start DPDT switches. Okay, so first of all, I don't think that we need to discuss about what a switch is because everyone knows it. Switch is basically a component to turn on or turn off any circuit. Okay, so we use switches for that purpose. So let's move directly to the types of switches we have. Okay, so we have SPST, SPDT, DPST and DPDT switches. Okay, so the full form is like single pole, single throw, single pole, double throw, double pole, single throw, or double pole, double throw. Okay, so let's understand what this thing is like pole and throw. What exactly they mean? So, pole. A pole indicates that the number of circuits which we can control using a particular switch simultaneously, like at a one time. Okay, so if here it is like double pole, it is written, so we can control two circuits at a time using that switch. Okay, so this is the meaning of this pole. Okay, and throw means which indicates that number of contact points in a switch. Let's understand this in our next slide. Okay, so first of all, let's see, it is single pole, single pole, single throw. So here, single pole means it will control only one circuit for at a time, and single throw means that only one contact point. So let's see here, we have one terminal at both the sides. Okay, so we can connect one circuitry over here, and at the same time we have this one contact point here. Okay, so that's why it is called as SPST, single pole, single throw. We can control one circuit and the contact point is also one. So it is single pole, single throw. Now single pole, double throw. In this switch, we see we are still having this one terminal to that side, so we can control one circuitry using this port. Okay, and we have two contact points, like this toggle. Once it is attached to this top position, so it is connected to this point, and when it comes down, it will be connected to this second point. Okay, so we have two contact points and one port for our circuitry. So that's why it is single pole, double throw. Okay, now double pole, single throw. So as the name suggests, double pole means it can control two circuits, and still we have single throw. That means it has one contact point only. Okay, so we have two terminals at both the sides. Okay, so we can control two circuits simultaneously, but still you can see like if this toggle is at this position, like if it is turned upward, so it is not getting connected to any terminal. Okay, similarly this bottom toggle is also not getting to any terminal. You guys might have this confusion that it is connected to this, but it is not. Okay, so this toggle is not connected to anything, any of the terminals. Okay, So we are still having single contact point here. Similarly, single contact point here for this toggle. Okay. So we have double pole as the name says. So we can control two circuits and one contact point. That's why the name is DPST, double pole single throw. Okay. Now DPDT, double pole double throw. So by double pole we mean that we can okay, this one is just a mistake, I think. Okay, this should not be there. Okay, so double pole double throw means we can control two circuitries simultaneously. Okay, but we have two contact points also. Like if this toggle is connected to this point, then it is connected. If these 2 points are connected, then in another configuration these 2 points gets connected. Okay, so that's why it has double throw also. So and similarly here it is one contact point here and one contact point here. Okay, so it is double pole because of these two circuitries we can connect, and double throw because we have two contact points. Fine. Till now, do you guys have any doubt in this SPST DPDT? I think this is very basic thing. There should not be any doubt, but if it is, please let me know. Any doubt in this thing? Okay. Okay, let's proceed. So we are moving ahead with DPDT switches. Okay. Directly we are going to discuss DPDT switches. It's just a basic thing. We will be able to understand. Just wait for some minute. A DPDT switch, as the name is, double pole double throw switch, is a type of electrical switch that has two separate sets of contacts and can control two independent circuits simultaneously. We have already discussed this in our previous slide. Okay. The DPDT switch is known for its versatility and is often used when you need to control two separate electrical paths or circuits with a single switch. Basically, it's just same thing. We discussed this in the previous slide. Okay. So it allows you to select between two different states or actions by moving the switch, actuator or lever. So here we are having this thing. This is called actuator or lever. If we press the switch, then the actuator lever changes its state. Okay. So in the market, we see DPDT switch in various forms. Like these are all DPDT switches. Physically, if you see the physical appearances of these three switches, I want to ask you one thing. What do you guys find common in these switches, in all these switches? Please. Yeah, they all have 6 terminals. Okay. Yeah, that was I was expecting. So they all have 6 terminals, and these are all DPDT switches. Okay. So it can be in this form, like we can press it here or here. This switch is just a basic one. This is push switch, push and pull switch, and this one is the sliding switch. Okay, these are all DPDT switches. Okay. Let's understand internal structure of DPDT switch. In DPDT switch, we have 6 terminals like this, this, and this. These are all terminals, and we have 6 terminals. Okay. So internal structure. Let's explain this thing. So if we turn this toggle to this side, left side, okay. So basically we are just, if we are turning it to that side, so this metallic strip gets set to this thing, and these two terminals are getting connected, and these two terminals are getting connected simultaneously. Okay. Similarly, if we are if you are toggling it to that side, so these two terminals are getting connected and these two terminals are getting connected simultaneously. Okay, so this is just basic working of DPDT switch. Use of DPDT switches. So DPDT switches are commonly used in electrical and electronic circuits for a variety of purposes, such as reversing the polarity of a motor, changing the direction of current flow, or switching between two different circuits. Okay, so I want to ask you one thing. You guys know DC motor. So how do we change the direction of rotation in a DC motor? By changing the polarity. Okay. So for those who don't know, let me tell you quickly. If there is a motor, okay, and this one is motor, and if we have connected a battery here, okay, if we have connected a battery here, so suppose in this configuration this motor rotates clockwise, then if we reverse the polarity, like if we change the polarity of this battery like this, so the polarity will also, so the direction of rotation will also be reversed. Okay. So in this way we can change the direction of rotation of a DC motor. Okay. Now we are going to use DPDT switches to change the direction of rotation in motor. Okay. We are not always supposed to change the polarity of a battery physically. We need some kind of switch so that we can, when we press it like this, so the motor rotates clockwise, and when we press it another way, so the motor rotates anti-clockwise. Okay, this has some application in RC car also. You can say forward and backward movement of a car we can control using a DPDT switch. Okay, let's see. First of all, okay, leave that thing first. Let us understand this basic circuitry first. Okay, we are going to control these two circuits simultaneously using this DPDT switch. So you guys might be wondering, how is this a DPDT switch? So this is just a top view of this DPDT switch. Okay, yeah, this. Okay, so this part is, so the top view of this is shown here, and okay, so as you already know, here we have discussed that if we toggle it to that way, these two terminals are getting connected. If we toggle it that way, then these two terminals are getting connected. Okay. So, if we toggle it to that way, okay, so we are basically connecting these two terminals and these two terminals together. Okay, what happens? So this circuit becomes complete. Okay, this circuit number 1 becomes complete, and this circuit still remains incomplete. This is open here. Okay, so the bulb will start to glow, because we have toggled it that way, so these 2 points are getting connected, so this circuit is getting completed and the bulb will start to glow. Okay, okay, but what if we toggle it that way? Let me change the color of the pen so that you can understand it better. If we toggle it that way, then these two terminals are getting connected. Okay, these two terminals are getting connected, and now these two terminals are open now. Okay, as we have seen here now. Okay, so if we toggle it that way, these two connected, then this is the same thing. Okay, so if you are toggling it that way, so these two points are getting connected. Now this circuit is getting completed and this circuit is open now. Okay, so this circuit is now open. So will this bulb glow in circuit 1? No. Well, it is an incomplete circuit. Okay, so this will not glow. Okay, fine. And this bulb will glow. It is getting completed by this toggle. Okay, fine. So basically, it's just a very basic form of circuitry. We have just explained controlling two circuits simultaneously using DPDT switches. Okay. Okay, coming back to this part, like we have seen that we have some DPDT switches application in reversing the polarity of a motor. Okay, so now let's say our aim is to reverse a motor polarity, like reversing the direction of rotation of a motor. Okay, so we need to change the polarity across its terminal to reverse its direction. Okay, so now we are trying to achieve this thing. So let us try to achieve this thing using single pole, single throw switches. Will be required 4 SPST switches for this configuration first. We'll move to DPDT switches later on, but let's understand using single pole, single three switches first. Okay, so in this configuration, what we are doing is we are having 4 SPST switches. SPST switches are just these switches, like single pole and single throw. One contact point. This is single pole and single throw switch. Okay, so these are all SPST switches. If we turn on this switch and turn on this switch, okay, and leaving these two switches turned off, so what happens is that this circuit becomes complete. Let me explain how. The current from this battery goes up and it follows this path, okay, and it goes through this way, and then it goes upward, then it enters motor. Okay, and as it reaches motor through this into this terminal and positive side, so this is the positive side. Okay, and now negative side. If this part is going like this, negative part, so here it follows, here it is open, so we don't need to go upward, we are going downward, and this comes back and it reaches here to this terminal. Okay, so this point is negative now. Okay, suppose in this configuration the motor is rotating clockwise, let's say. Okay, in this configuration, let's say motor is rotating clockwise. Circuit is getting completed, so motor will rotate in anti-clockwise or clockwise. Okay, so let us say this is rotating clockwise direction, in clockwise direction. Okay, now we are changing the configuration. Now we are like, if we have turned these two switches on and turning these two switches off, now what we do is turn on these two switches and turn off these two switches. Okay, let's see what happens. Okay. Okay. Earlier we turned on these two switches. Now we are turning on these two switches. Fine. Okay. Now the circuit is again getting completed. Let's see how. The positive terminal, the current flows through this direction and goes here, and it reaches here, and through this pathway it enters the motor. So now this point is positive. Okay. And from the negative side, if you see, so here it goes through this way and it reaches this terminal of the motor. So it is now negative. Fine. So now you can see, like when we change this configuration, the polarity of the motor is also getting reversed. So the direction of motor is now reversed. Earlier it was rotating clockwise. Now it will rotate anti-clockwise. Fine. So we are just using this commutator circuit, it is called, to change the direction of rotation of a motor using SPST switches. Okay. Now let's understand this using DPDT switches. Like we will be requiring, if we use this configuration, we'll require 4 SPST switches, and at the same time we have to click so many buttons. Like we have to press this on and turn these two off. Better if we can have something like that, that if you press this button that way, so it is forward, and if you press it that way, so it is reverse. So better if we have this thing. So we will not use SPST switch for this thing. This is so tedious to govern this. Okay. So let's move further. This commutator circuit can be also made through DPDT switches. Now let's see DPDT switch. Here you can see that if we consider these 2 points, okay, don't you guys have this like sort of feeling like it is something like a SPST switch having these 2 things and these 2 things separately? Okay, so we are just using this thing here. So now we are trying to make this using DPDT switch. Okay, here you can say when we are turning, as here we have already seen, as we are turning this switch on, so at the same time we are turning this switch off. And if you are turning off this switch, we are turning on this switch. So simultaneously these 2 switches are not getting turned on. So we are turning this on either and turning off this. Okay. So we can do this using DPDT switch. In DPDT switches, we have already seen that if we are turning on these 2 switches, these two terminals are not connected. So this is the in-off condition. Okay. 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 So we are just trying to have this configuration practically in our DPDT switch. This is basically just our DPDT switch as seen from the top. Okay, so this is the top view of DPDT switch, and if we toggle it to that way, let's say, suppose, what happens? We are basically having 6 terminals like DPDT switches. So we are connecting motor here. Motor is connected to this terminal, like motor is connected to this switch and this switch. So here the motor is getting connected to this terminal and this two terminals. Okay, this is just a simultaneous model, like these two things are showing the same thing. Okay, and if this side of the motor terminal is getting connected to these two terminals, here it is also getting connected to these 2 points. Okay, and battery is connected here. Okay, so here is also this battery is connected to these 2 terminals. Okay, now if we toggle it to upward side, so what happens? These 2 terminals are getting connected and these 2 terminals are getting connected. Okay. Now, can you guys tell me, is it going to work? Do you guys think, is it going to work? If no, then why? Give me some valid reason.
Louder, please.
Yeah, anything, any answer you can say. Just say one thing. Let me give you. Okay, you're saying something? Anyone? Like anyone is having answer, like why it is not going to work if we are toggling it backward. So why this motor will not work, or why are we not supposed to have this switch, or if we are not, if it is not working, then why?
Polarity will not change.
Polarity will not change. Yeah, that's the thing. And okay, if we want to have, let me tell you, let me explain this thing now. If we want to have this configuration here, as you can say, here this switch is turned on, no sorry, this switch is turned off, and here this switch is turned on. Okay, but here what happens? These 2 terminals are getting connected, so both the terminals are getting turned on. Okay, so this is not the simultaneous version of this thing. This is not working exactly the same. Okay, so we are not going to use this. So we have to do some modifications in this. Okay, it will not change the polarity, as you said. Okay. Okay. So what we are doing now, we are just using this DPDT switch, and firstly we are connecting, like, let me explain this here. Paper. Okay. Now we are changing the configuration of our DPDT switch. Like if this is the top view of our DPDT switch, we have 6 terminals here. Okay. And what we do now is, firstly we connect these 2 terminals diagonally. Okay. Connect these 2 terminals diagonally and these 2 diagonally. Okay. And now rest of the configuration remains the same. Like we are connecting motor here. Okay. As we already had this configuration here also, so we were connecting motor to this terminal and this terminal. Okay, so we are having the same configuration, just we are having this diagonal connections first. Okay, so now what happens is that now we are connecting battery, just same as we had seen here. We were connecting battery to this mid terminals. Okay, so this middle terminals we are connecting battery to it. So now we are connecting battery to it. Now, let's see what happens. Let's start again. Let's look into the voltage flow, current flow direction. Okay. So, if this circuit, if we toggle it upward, right? If we toggle it upward, now the same thing is shown here also. So we can see this thing in the slide also. Okay. So if we toggle it upward, like if we turn on this switch with this configuration, DPDT switch is getting turned on using this toggle moving upward. Okay. So what happens? These 2 terminals are getting connected and these 2 terminals are getting connected. Okay, we cannot change this thing, like we cannot have this toggle upward so that one terminal getting connected here and one terminal getting connected here. We cannot have this thing. It is already here in this internal structure you have already seen. Oh, let me erase something. So if you are toggling it this side, so these two will connect and these two will connect. We cannot have this thing, like we cannot toggle it here and one getting connected here and one getting connected here. Okay, so we are just modifying our configuration now. Where is the pen here? Function of line. Okay, so now if we are toggling it upward, let's say, okay, just let me erase something. If we are switching this circuit upward, so these two terminals are getting connected and these two terminals are getting connected, and now we see the current flow direction. Okay, so here the battery positive terminal current flows through this direction, in this direction, and it follows this path and goes here, then comes here and it enters to the motor through this terminal. So this side is positive, fine. And if we see the negative side, so here negative side is here. Okay, so it follows this path and goes through this path. Sorry, not this path. Let me correct it again. Not this path. It is open here, so it will not go anywhere after that. So negative part will follow this path. Here it will go like this and directly getting to this upward side and entering to the motor. So this part is negative now. Okay. Now motor will start to rotate, and the direction, let's say again it is let's say now it is anti-clockwise in first case if you are toggling it to upward direction, so it is anti-clockwise, let's say. Okay, now what we are doing is just take another configuration. What if we toggle it to the downward direction? Okay, so if we connect these two terminals, like if we toggle it to downward direction, so these two terminals are getting connected and these two terminals are getting connected. Okay, now just follow the current flow direction. So current will move here and it goes here and follows this path and reaches to this terminal. So this is positive now. Okay, and what about this negative side? So negative side, it will follow this path and goes here and it directly reaches to this. Okay, so this is negative. Okay, so as you guys can see, earlier it was this polarity and now the polarity is just reversed. So the direction of motor is getting reversed with this configuration. So we can use DPDT switches in this configuration. Okay, so okay, let me switch. Okay, so this is just the basic configuration. We can use DPDT switches to control our direction of motor, and it has various application in our cars or anything which we want to rotate in either ways, like anti-clockwise or clockwise according to our control. We can control it using DPDT switch. Okay, so do you guys have any doubt? I forgot to ask you these things. Are you guys getting it clearly? Okay, so yeah, that was from my side. Any doubts?